All right, the light is on. So what we need to do today, it's a short lecture, so we are going to discuss mostly about hierarchical Bayesian analysis, which really summarizes many of the things we have discussed up to now in the course. So it's extremely important topic, and in addition, it's part of your homework. So let me just rapidly go through these basic type of prior models that we have seen. Let me see. So we discussed about informative priors, and mainly we spent time discussing about conjugate priors, and particularly those that belong in the exponential family. We defined what it means to be a conjugate prior. I'm actually curious, does anybody even bother to hit the Wikipedia to see the nice website we have on conjugate priors? Yeah. You did? It's very nice. I mean, that huge table with all the information is just amazing. Okay? It's just amazing. All right? So effectively, if the posterior takes the same format as the prior but with updated parameters, we call that prior to be conjugate to the likelihood or the class of the likelihoods that we work with. And we gave lots of examples. And for those that have not seen this type of things, distributions from the exponential family, everything like that, I will advise you that you actually search to find more information, because this is a topic that we will come back to generalize things later on in the course. Okay, so this is sort of just the way. We haven't discussed anything about the properties of the exponential family. We only gave the general structure, so there's much more than what you see up there. All right, so we gave a few examples, etc., etc. We sort of said that these priors, we can interpret them as giving rise to pseudo counts, or pseudo measurements. You don't really need that explanation, but that is typical, basically, something that goes with the exponential family. All right. This is a very fundamental property. We said that if two distributions are conjugate to the likelihood, and you take a mixture of them, then the actual posterior distribution is also conjugate. I'm sorry, the posterior distribution has the same form as the mixture of the prior. In the prior, the only difference is the weight coefficients now are posterior weights. All right? And we gave a very nice simple calculation in one slide on how to compute those posterior weights. Now, this calculation in general in the example that we gave looks simple, since you can compute the evidence basically that you need to compute these posteriors. You need this the probability of the data, right? This normalization factor from Bayes' rule. So in this example, there is an analytical expression. In other computations, this may be a little bit more lengthy, and that's why this is not something basically that we see often in the literature, even though it's very powerful, because in essence, a mixture of two conjugate exponential type of distributions can give you any complexity that you would like to have, right? So if you really are concerned about the information you introduce with a prior, and you take a mixture, then you're all set, but the complexity will go up exponentially. Okay, so that's something you need to be concerned. All right. We discussed about an informative, non-informative priors and informative priors, and we mentioned and we show it actually through the Jeffreys prior that beta 1,1 is actually not the best uninformative prior. It's beta 1/2, 1/2, right? So remember that when you do examples. We said that we need to be sure that reparameterization is taken care of in consideration when we introduce those non-informative priors. So don't go and use something that is uniform, and then somehow in your calculations from uniform you get something else weird that is not what you originally had in mind, okay? And so this is a summary of the change of coordinates, if you like, in the parameterization of these priors, how it looks like. We introduce the translation invariant prior that is basically used mostly to describe the mean of distributions, and it is a uniform distribution, right? It's a constant. And so it's improper, it does not normalize, but somehow, if you have one measurement, you can normalize the posterior so that solves in part your problems. So translation invariant means if you move if you try to compute the probability mass from A to B and you shift that interval by an amount C, the probability mass doesn't change. And then we define the scale invariant prior, and here we don't translate, we change the scales from A to B to A over C to B over C, and you can show through the calculations on the slide that for the scale parameter, the prior is 1 over sigma. And again, if you're going to use this for sigma square, it comes out P of sigma squared is also 1 over sigma squared, right? So you can do this for sigma or 1 over sigma squared. It's the same thing. So don't mix this with P of sigma squared being 1 over sigma that some people use in the literature for the wrong reasons. So P of sigma is 1 over sigma, P of sigma squared is 1 over sigma squared, okay? So this is an improper prior. Okay, let me see. And then just to finish up the summary, we introduced the Jeffreys prior by taking this expectation with respect to the probability of the data of the second derivative with respect to the parameters of the log likelihood, and then taking this matrix, taking the determinant square root, that's the prior, that's Jeffreys prior, and it's a little bit unusual because it violates some of the principles of Bayesian thinking since it depends on the data, but somehow it comes out that it has nice features. So when you change the parameterization, automatically, basically, it accounts for that. Okay, you can see that derivative there, the chain rule basically gives you the change in the volume induced by the parameterization. If you use Jeffreys prior for the mean, you get exactly what the non-informative prior we have seen. You get a uniform pi of mu. If you do this for a scale parameter, you get exactly what we have seen before. And this is, for example, P of sigma squared is 1 over sigma squared. So really, the non-informative priors, we could have not bothered them to discuss them separately, introduce them as part of this Jeffreys non-informative priors. Okay, don't need any of this. And we said a word only that somehow, whatever prior you use, be sure that it does not affect to a significant degree your posterior distribution, and that means you need to be sure that your results are robust to the prior choice that you have made. Okay, and so this is actually a data set that is it comes from Robert's book. You can click there. It's obviously a Gaussian data set, so the likelihood is Gaussian, and we use priors, one that is flat and another one that is Gaussian with around 0 with some small variance, and you can see the posterior changes significantly. And in this problem, if I remember, you have lots of data. So if you have lots of data and a small change in the prior makes such a change in the posterior, that's an issue that you need to be concerned. All right. And just so that this will come back when, to a significant degree, basically, when we talk about regression, let me only say the following thing. These robust priors have heavy tails, okay? And in essence, they try not to pull you towards the prior mean, okay? And so when you see ideas later on of using a Laplace distribution as a prior or a Cauchy distribution instead of a Gaussian. The reason for that is robustness. Okay? So affiliate robustness with heavy tails. And as we have discussed maybe in another course, having these distributions with heavy tails, they are also less prone to outliers. So if you have a data point that is wrong and it's out of nowhere, these prior distributions are robust and don't affect things just because you have seen a weird point. Okay, so we start now this new topic. The slides are very few, but I think the presentation is sort of, the calculations are a little bit heavier, but the topic is extremely fundamental to Bayesian analysis, so hopefully in the 40 minutes we have in this lecture, we can cover this and make some sense out of it. Okay, so let's look at this equation, right? So you have some likelihood, and you have some parameters in your model. So the parameters, we call them up to now theta. But if you remember, let's say, if we say we're going to use a beta prior has parameters alpha and beta. So how do you select alpha and beta? Do you just put any numbers there, right? So I call those parameters that the prior on theta depends, I call them phi. So you can think, when you toss a coin, the prior for theta depends on A and B is phi. Okay? So what that leads is, effectively leads to additional parameters. So yes, you have theta, but now you have also the parameters phi, because theta depends on phi. So in principle, when you talk about the posterior of the parameters, you talk the posterior of theta and the posterior of phi. And if you write this as the likelihood times the prior, remember the likelihood depends only on theta, and theta depends on phi. So if you know theta is sufficient to describe the likelihood like that, okay? And this joint prior is written as the prior of theta depending on phi. So in the coin toss problem, this can be our, let's say, beta distribution with parameters alpha and beta. And pi of phi is the prior now of the parameters that come in the prior of theta. So this is a hierarchical model of two levels. All right? What is the purpose of using a hierarchy of models? You want to increase the complexity of the model and its representative capability, if you like, but also you want to make the effects of the prior on theta less prone to your calculations. So if you're not confident on theta because you're going to have to set some parameters phi there, you say, you know what, let me assume another distribution over phi. And if you're not confident on phi, let me put another distribution over phi. So that's how you get hierarchical models. But there is a more fundamental reason for doing this hierarchy that we will discuss today. All right? You will have to appreciate this through examples. I'm going to wait to introduce some examples before you see the more fundamental reason for doing hierarchical model. So let me just write, here is a prior that involves basically, so you have a hierarchical model where theta depends on theta 1 on theta 2, etc. So pi of theta really requires, if you really want to get only the prior of theta, you need to integrate all of the other hyperparameters out, okay? Which is not going to be possible. It's going to be a very difficult thing, right? But in principle, if you only care about pi of theta and theta depends hierarchically through all of these other variables, you're going to have to do some integration like that. So if we concentrate on a two-level hierarchies, effectively, the fully Bayesian analysis is this first equation. You're going to have to basically compute the posterior of all the parameters in your problem. So if theta depends on theta 1, you're going to have to compute the posterior of theta and theta 1. That's fully Bayesian. Okay? And notice again, the likelihood depends only on theta, because if I know theta, sufficient to know x, right? Theta depends on theta 1, and then you have a prior on theta 1. So that's the full model that somehow we will try to avoid today by doing some tricks. Okay? So we will try to avoid doing this calculation where we compute the full posterior. The other things that actually we already have done up to now is when we calculate the posterior to actually condition them on θ1, right? So for example, when we did the toy cos, you know, the coin example, and we said there is a prior on theta that depends on parameters A and B, we assumed we knew alpha and B. So really what we did is we computed a conditional posterior given alpha and beta. All right? So this is not really very good because, like, okay, given, from where do you get those numbers? All right? If you do something smart, of course, this may work. Okay, so if these are not arbitrary numbers, but θ1 is some specific educated estimates, then maybe you're okay. And of course, you know, like I indicate here, another way is to calculate the marginal posterior, where you compute the whole posterior, but then somehow θ1 has been averaged out. Okay? So again, this is the full Bayesian way of doing it. This is the conditional where you use some point estimate of θ1. So maybe what we will do, it may look at the end like the second model. And of course, this marginal posterior, that somehow to be able to compute this, you really need to know the full posterior. All right. So there's, I'm going to bypass this. Okay, so let me go through the specific example that you have to do in your homework. By the way, I really want to be direct on this, right? I know that students don't like to complete one sentence of wording when they submit homeworks. They just submit a program, one picture says done, okay? If you do this, and I notice, a Zurich sends me back to homeworks, and there is a problem where you just give me a plot, I'm going to change the grade and put a 0. I want to see a complete sentence that, in essence, you show to yourselves and to me that actually you did some thinking about this and you understand what's going on. It's not like press return and get a nice picture. And I'm saying this because you realize that it's more difficult to be able to put your thoughts in words and equations rather than just clicking return, okay? So don't submit me a homework, which means also don't submit me a homework solution, you know, that only contains the results. I want a discussion. All right, so let's see this hierarchical Bayes for the example that you have to work in the homework. You don't have to read everything that is there, so we will see this in many slides. So let's say that we have a number of cities, and some cities have big populations, some have small populations. So for city I, the population is called Ni, okay? So Ni is the number of people living in city I, and we try to actually estimate the cancer rate in every city. So we, let's say over the period of a year, we collect information, and in city I, the number of people who die from cancer, let's say it's Xi. Now, a good model for every city to compute Xi is to actually, you know, postulate a binomial distribution. So you say in population of Ni, Xi people have cancer, and θi is the probability of getting cancer in city I. Okay? So that's our standard problem. So the objective of this problem is to calculate the cancer rates θi for each city I. Okay? Now, the obvious approach will be, who cares about Chicago if I live in South Bend, right? I'm going to do this for each city differently, and I'm going to calculate the cancer rates independent for each city. And the obvious actually estimate for θi will be to use the MLE estimate for the binomial distribution. And what's the MLE estimate? Which is sort of the common sense estimate. So if in a city of Ni population you get Xi cancer, what's the common sense MLE estimate? Xi over Ni, okay? All right, so, I mean, that would be the first thing everybody would do, right? So that's a respectable answer. Now, the problem is the following. how about if you have some cities that have very small population, all right? And as a result, the number of people who die from cancer is very small. Will you actually trust the testing? Because in other words, nobody died that year. Will you say that theta I equal to 0? All right? So the idea here is that somehow we want to pull the information that we have from all the cities all together and somehow make these theta i's in the different cities to depend on each other, to share strength basically with each other. So how do you do this? Well, you do this by introducing a prior on these theta i's that depends on some parameter theta, right? And we already have discussed this for the binomial distribution. The conjugate prior is a beta distribution, right? And in what we discussed in earlier lectures, we set the parameters A and B of this prior distribution. So we already have done this. So we need something a little bit different. The point here is, if you fix alpha and beta, are the parameters theta i's for the different cities independent or dependent? If you say, alpha equal to 0.2, beta equal to 3, are the parameters theta i's are coupled because this distribution depends on eta? No, they are not. They are independent samples from a distribution with given parameters. Yes, I give them to you. So I give you a distribution with specified parameters alpha and beta, and then you're going to take samples from it that they are IID samples. Okay? So if you fix the parameters, these cancer rates that you want to compute, they're basically independent of each other. So there's no way you can share information between cities to estimate all of them. So what you need to do is, you need to find a way where somehow these parameters theta are computed from all the data. Okay? Not of one city, but all the data that you have. Okay? And to do this, you're going to assume that this theta is basically a random variable that you don't know. It's a hidden random variable, all right? And somehow, whatever you are going to say about the random variable, all right, it has to be said by using all the data in all the cities. So using basically all of the NI's and all of the XI's. So somehow, if eta becomes a random variable that is computed through all the data, then all the parameters are pulled together, they are linked together because they depend on eta, and eta is computed through the data. Okay? It's not set by you, it's computed through all the data. All right, so let's see how the hierarchical model is going to look. So what I have here is, we have seen this equation, right? So I have the likelihood model. So this is a product over the cities, a binomial distribution, right? That's what we have. And we put the prior for each I is a beta distribution. And now we put a prior on eta, okay, that we denote as pi of eta. So before I show you the mathematics of this, right, you just keep in mind that somehow we're going to have to link and compute and say something about eta by utilizing all the data. Okay, so I'm actually, let me, so I took this example that's coming from a paper actually, but there is a brief discussion of this in Murphy's book. So let me try to describe the actual methodology that somehow it is going to be used to get the pictures that you're going to see in the picture to come, in the next two pictures. So what we're going to do is, because we have a hierarchical model, and the first parameters are theta, and then theta depends on eta, the effect, first I have less parameters theta, you notice, than theta. It's very important. So I don't, there's no way that we will overfit whatever we do with this parameter theta, because there, we don't have too many parameters theta we don't have too many parameters theta as theta. right? So we can have 50 cities, but eta here is only 2 parameters. So what the idea here is the effect of theta on our estimations and predictions is less severe than the effect of theta itself. And because of that, and because we know there is less chance of overfitting, we can actually use a point estimate of theta and simplify this equation. So effectively, rather than taking eta to be coming from some distribution pi of theta, find one point estimate, one particular value, and fix theta, but that particular value has to be computed in a way that utilizes all the information in all the cities, thus linking all the theta i's together. All right? So we're going to use a point estimate of theta, all right? And that point estimate has to be computed using all the data. Okay? So can you imagine, and we will see the equations after I show you the example, can you imagine, when we want to compute any parameters, there is only one criterion in Bayesian setting that we have seen in the last 2 lectures. The only information we have is data, right? And when you want to select some parameters, in this case some point estimates of alpha and beta, the only information we have data, and what information the data provide that somehow we want to maximize. You remember all these concepts of model selection and this and that, so what is the information that we want to maximize if we try to compute any parameters?
Let's do a parameter based on data.
Not a posterior, so we have data, right? And we have a model from where this data are coming, right? So if we're going to select some parameters, those parameters need to be such that they maximize what? The marginal likelihood of the data, the evidence, right? So basically, what we need to do here is, we're going to fix eta to some point estimates, and so what we're going to do is, we're going to integrate this equation in theta, in all the thetas. So what effectively we're going to get out is we're going to get out actually the likelihood of the data. All right, and because we're going to fix this at one point, right? So we're going to get basically P of D, and then we're going to have to maximize P of D with respect to the parameter theta. So we can find one point estimate that we can plug in this expression here. I am going to show you equations exactly on what I am talking, right? I'm just saying right now, the effect of theta is not as severe for overfitting as the effect of theta. So what we will do is, we will use a point estimate for eta, and that point estimate will be computed by maximizing the evidence of the data. And that methodology is called Empirical Bayes method. Okay? So the Empirical Bayes method is, you use a point estimate for the hyperparameter theta, and that point estimate is computed by maximizing the marginal likelihood or evidence that is computed from this equation where theta is integrated out. So let me motivate first what happens and why are these concepts important for this particular example. So you're going to have to derive this, and you're going to have to check. Don't trust any of the symbols that I have put in equations, because most probably the actual programs that Murphy has that you can look at, maybe they're not consistent with what I think the methodology is. So you will have to figure out and write down both the theory and the modeling to be sure that we're consistent. So what you see on the top is the number of people having cancer on the 20 cities, okay? So you notice there is some cities basically have 0 cancer. So no, you're not going to go and put and say the probability of getting cancer in those cities, let's say city 11 is 0, because it just data say there's nothing there, right? In some other cities, you notice where the population is very big, you have lots of samples and lots of people getting cancer, right? So this NI is the population of the cities, right? Some big cities, some small cities. The third row is the MLE estimate, and the MLE estimate is completely independent for each city. It's really xi divided by ni, okay? And this little red line is what's called the pooled MLE. So basically, if you compute one cancer rate, right, using all the people that have cancer in all the cities divided by the population sum of all the cities, you get this red line, okay? So again, when you look at the MLE, in places where you had no xi was 0, you basically get 0. It's like too bad. Now, if you use the pooled MLE, those zeros are being elevated basically, and everybody is getting the same value. So even the cities that had high cancer rates, right, now are being reduced down to something there. So it's like a compromise. Some are being elevated up, some are pulled down significantly. So this is not really a very good estimate, okay? The best estimate you can get is doing this idea that I mentioned of the empirical Bayes, where you fix the parameter zeta to values that are computed by maximizing the data likelihood and the marginal likelihood. And then once the parameters zeta are fixed, you can go and you compute the posterior of the parameters theta I. And we already have done this on lecture 2, I believe, on discrete data, right? If you have a binomial distribution for the likelihood, you have a beta for the prior, right, for given parameters eta, you can compute the posterior. That is also a beta distribution, by the way. And this is the mean of the posterior. You can see, given the data, this is the mean of the posterior. And you can see the mean of the posterior, it's everywhere non-zero. So even in the cities where the cancer rates were 0, you don't get any 0 now. Why? Because you don't rely, for example, on cities 16 or 17, you don't rely on the information locally to make decisions. You fixed all the parameters, the parameter theta using all the data. So effectively, the estimation of the parameter theta I of the posterior depends basically on all the data, not just the data of CTI. And as a result of that, the estimates are way more reasonable than what you will get with an MLE estimate on row 3. And I'm going to give you an exact, actually, equation, not for this problem, but it's actually the same equation. For the second problem, you will see exactly how the posterior looks like, but you can guess that this posterior will be sort of a convex average of the MLE estimate, and what else you think? So it needs, remember, whatever we get, right, it needs to contain information that comes from all the data. So when maybe it's already in the slides on lecture 2, if you look at the posterior mean for binomial beta prior, the posterior mean is the average of the MLE estimate, and some MLE estimates are 0, and of something else. And the something else, maybe you will say, what will you say? So it's an average of the MLE, and what should the something else be? What will you think may be coming? Like when we did the generic analysis early on, the posterior means were coming to the average of the MLE and, I mean, in lots of the estimates we have seen, it is the MLE and something else. What is that something else? I mean, this is a Bayesian analysis, or there's priors there. So what is that something else? What other information there is beyond the MLE when you do Bayesian analysis? MLE is the data. So what else do you have there? The prior, all right? But you remember now, the prior that involves parameters alpha and beta, those parameters alpha and beta depend on all the data and have been fixed by maximizing the evidence, all right? So this prior is what we call the population mean, is the prior of theta with this parameters alpha and beta fixed by using all the data. And I remind you that the prior of theta, if it is a beta distribution, the prior mean is alpha divided by alpha plus beta. And that's why I have written this here as the expectation sort of alpha divided by alpha plus beta given all the data, to emphasize that these alphas and alpha plus betas are computed by maximizing the evidence of the data. So again, the posterior mean is the average, the convex average of the MLEs, and some of the MLEs are 0, and also this pooled mean, so the prior of theta, if you like, where the parameters in theta have been computed using all the data. Okay? So let me go a little bit further, and you will do this example to see exactly what is going on. So for this, what you see here is these little stars there are the posterior means. So basically, these are those values that you see here. And these are the 95% credible intervals from the posterior. So you notice, for example, CT15 has very small uncertainty. So can you see why CT15 has very small uncertainty? Is that reasonable? Look at the first two plots and see why CT15 has very small uncertainty. Say it again? Yeah, very big population and very reasonable number, very high number actually of cancer rates. So basically, you're very confident that the data that we have for CT15 are reasonable enough to actually make an estimate for CT15 without needing to use cities that have 0 cancer rates. So in some sense, even the MLE estimate for CT15 is very good, right? But what happens is, by utilizing the information that CT15 is giving you, you share the strength of CT15 to allow you to make estimates for the other cities. You see that? The other cities that don't have enough, basically, population and cancer rates are going to be using information extracted from CT15. But for CT15, the uncertainty is very small because we have very high information. And if you look, let's say, at CT19, has very huge uncertainty. So can you see why CT19 has very huge uncertainty? Okay, so CT19, all right, why does it have, so 19 is here, right? So 20 has 0 cancer rate. So why CT19 has a very, large uncertainty, posterior uncertainty? So the MLE for, when you compute the MLE for 19, right, it comes a very big value. All right, that's the MLE estimate. And remember, what is really happening in computing this posterior means the cities that have very high MLEs have to come down in their estimates. And the cities that have 0, very small, have to go up. So what's happening to CT19? The MLE estimate is very high, but this MLE estimate is way far away from the pooled MLE. All right? Or even this population mean, as I define it for the mean of the prior. So effectively, the MLE estimate tells you something, but the pooled calculations basically tell you that no, this is way too high. So basically, the MLE for the estimate for CT19 has to come down, and that's what it leads to very high uncertainty for CT19. Okay. So this really contains, I would say, all the essential elements of these hierarchical Bayesian models, and contains sort of everything more or less we have done up to now. It involves this concept of maximizing the evidence, all right? And here we maximize the evidence. So we integrate theta out, and then we maximize the evidence with respect to alpha and beta. because in the hierarchical Bayes model, we're not going to produce a posterior for eta. It's a very computationally expensive thing to do. What we're going to do is we're going to fix it at some point estimates, but this point estimates will be computed from all the data, and because eta is computed from all the data, these parameters theta now will become dependent on each other, so they will share strength to make the predictions more reasonable. All right, so here's the equation in mathematical forms of the things presented. So hopefully this equation will clarify things. So what we're going to do is we're going to approximate effectively the posterior of eta to some delta function, so some point estimates. So we will fix the values alpha and beta, and the point estimate basically is going to be computed by maximizing these, well, the way that I have it here, it says maximize the posterior of eta, all right? And here the posterior is the marginal likelihood times P of theta. Obviously, I'm taking as P of theta to be what? Since I'm going to fix it to a point estimate, I'm taking the prior to be an informative, uniform, right? So effectively maximizing the marginal likelihood is really like maximizing the posterior of theta, okay? Since I don't see, if it's not explicitly stated, but we take, oh, it says there a uniform prior on eta, okay? So we're just fine. So what you see here is the marginal likelihood, right? I mean, this is what we use for model selection. We integrate the parameters theta out, and so this is the evidence. So, but now we express the evidence as a function of the parameter theta. And the idea is go and optimize this, compute the derivatives with respect to eta, okay? Where eta is the parameters alpha and beta, and then set in your calculations, set the parameters theta to those fixed values. And this is what we call empirical Bayes and evidence procedure, type 2 maximum likelihood, and other names depending on what types of books you read. Okay, so this is sort of very, very, again, fundamental problem and approach for hierarchical Bayesian models. All right, somehow the time passed faster than I thought. So the summary of 4 different possibilities that you can do, all right, up to now. So one thing is you can do maximum likelihood, right? You maximize the likelihood by, and so the parameters, you compute the parameters theta hat that maximize the likelihood. The other one is you maximize, you do the map estimation for some given parameter theta. This is what you see here. Now, the other one is you fix the parameter theta by maximizing the evidence. This is the empirical Bayes, the third line that we discussed today. All right. The fourth thing is, you know what? Don't maximize the evidence. Actually, maximize the posterior of theta. So in addition to the evidence here, you're going to have a prior of theta as well. So this will be the same as maximizing the posterior of theta given the data D. Okay. And of course, if you want to really be Bayesian, you take everything to be a random variable and you compute the posterior of theta and eta. Okay? And if eta is a nuisance parameter that you don't really care at the end of the day, you're going to have to marginalize the last equation and integrate eta out. All right, so let me, so in this particular problem with the culture rates, right, the marginal likelihood, we have seen it explicitly in a few of the lectures, and I remind you, the way you calculate the marginal likelihood is effectively a ratio of normalization factors of the likelihood prior and posterior, okay? And I think we discussed about this for the binomial beta distribution on the last lecture as well, okay? Now, obviously, when you write the likelihood like this, in your homework, there must be some way to compute to optimize this with respect to A and beta, and the reference is basically written, it's, I'm assuming this report of Minka, and most probably Subik gave you the program, right, to do this optimization, but out of curiosity, you may want to actually look at it because tomorrow you may want to generalize this to something else, okay? So certainly you don't have to do this analytically, so if you find some numerical way of doing it, you can do that as well. All right, let me, we have literally only 5 minutes, okay, so I cannot really, maybe we need to come back to this. So let's do a more interesting calculation where the likelihood is a Gaussian and the prior is also Gaussian. In many ways, the same problem as what we have seen with the cancer rates, but now we play with Gaussian, so no more discrete models. So what we do is we have schools, D schools, so J equal 1 to D, and in each school we have nj students, index I from 1 to nj, and we want to estimate the mean score for each school, and we call that theta j, all right? So the students take different exams, and we want to basically, let's say they take you know, a particular class or something, and we want to estimate the scores, the score rates for each school. Okay. So if you look at the you know, unnormalized posterior, really what we have is the first two terms that you see here is the likelihood. You agree with me, right? You have these schools, and for each school, basically, you have MJ students, and the grades are following a Gaussian distribution with mean grades theta j for each school, which is unknown. That's what we want to compute, and with some variance sigma square. And I take sigma square to make things easy to be constant here. And we're going to put a prior on each theta j. So these priors are inside the product over j. So the prior has parameters mu and tau square, and immediately you can appreciate that the hierarchical Bayes analysis, what it will do is, it will compute point estimates of mu and tau square by maximizing the marginal likelihood, the evidence, right? And then once you fix mu and tau square to some point estimates, using all the data, then somehow you will be able to compute the posterior theta and the posterior means, and that will be a very good estimate for your analysis. All right, so the calculation, it's very tricky, and you know, if you read, you can go from paper to paper, right? You will see sort of different derivations, and the one that you see, in some sense, I found it, you know, on a sort of a wiki page of some individual on the website that somehow provided, if you like, the easiest way to come up rapidly with an answer to this problem. And the way is the following. You notice here, so we have a product for each school. We have nj students, and these are univariate Gaussians, right? So for each school, we have nj students, okay? And our interest is really to calculate theta j. So it comes out, if you multiply all these likelihoods for the individual grades of every student, the effect of theta on theta j is the same if you actually take one Gaussian where you pretend that you have only one measurement, which is the sample mean, all right? The sample mean, which you see here, and the mean is theta j, all right? And the variance now is not sigma square, but is sigma square divided by nj. Can you guess from which fundamental law in statistics this may be actually also be coming from? You remember what type of distribution the empirical mean follows? And what theorem says that? For the, you know, if you have the empirical mean, it actually can be of any distribution, in this case the Gaussian. The empirical mean of, you know, coming from any distribution. What distribution does it follow? It follows a Gaussian with mean, the actual mean of the distribution, which we want to compute, and a variance, which is sigma square over n. All right, so sigma j square is really sigma square over nj, okay? So what law says that of statistics? Central limit theorem, okay? So that way, you get rid of that product over students, and you can write the joint distribution of theta and the data. So this is sort of the normalized posterior. You can write as the product over schools of the prior times the likelihood, or now you treat the likelihood as 1 term, okay? Not product, because now you use the empirical mean, and that contains the same information that you need for theta j as using the individual xij's. So, I'm going to have to finish rapidly. So let me tell you, and we will come back on this on Tuesday. So effectively what you need to do is you need to calculate the maximum, the evidence, and then once you calculate the evidence, you're going to fix the parameters, mu and tau, to what you see here as mu tau and tau hat, okay? I'm not telling you from where they come and why they look in this form, but basically mu hat and tau hat will need to be selected such that you maximize the evidence. If you do that, the posterior means they come to be, you can see here, the posterior distribution is a Gaussian, and the posterior mean is an average of the pool mean, if you like, of over the grades for all the schools. And what is xj bar? The MLE estimate for school J. Okay? So I will stop there because 12:21, I don't want to cut the presentation. We're going to come back to this. This, what you see, is what is called the shrinkage effect to stabilize this type of calculations with hierarchical Bayes, and it is fundamental to practically everything in Bayesian analysis. So you may want to read this example, and there is another little example related, you know, and we will come back to it on Tuesday.